When looking at a typical airfoil, such as a wing, from the side, several design characteristics become obvious. You can see that there is a difference in the curvatures, or camber, of the upper and lower surfaces of the wing. The camber of the upper surface is more pronounced than that of the lower surface, which is usually somewhat flat. The two ends of the airfoil profile also differ in appearance. The end which faces forward in flight is called the leading edge and is rounded. The other end, called the trailing edge, is narrow and tapered towards the rear. The chord line is a reference line drawn from the center of the leading edge straight through the wing to the trailing edge. The distance from this chord line to the upper and lower surfaces of the wing shows the magnitude of the upper and lower camber at any point. Another reference line, drawn from the leading edge to the trailing edge, is the mean camber line. This mean line is equidistant at all points from the upper and lower surfaces. An airfoil is constructed in such a way that its shape takes advantage of the air's response to certain physical laws. This develops two actions from the air as it passes through: a positive or high-pressure lifting action from the air mass below the wing, and a negative pressure lifting action from low pressure above the wing. Different airfoils have different flight characteristics. Many thousands of airfoils have been tested in wind tunnels and in actual flight, but no one airfoil has been found that satisfies every flight requirement. The weight, speed, and purpose of each aircraft dictate the shape of its airfoil. The most efficient airfoil for producing the greatest lift is one that has a concave or scooped-out lower surface. As a fixed design, this type of airfoil sacrifices too much speed while producing lift and is not suitable for high-speed flight. On the other hand, an airfoil that is perfectly streamlined and offers little wind resistance sometimes does not have enough lifting power to take the airplane off the ground. Thus, modern airplanes have airfoils that strike a middle ground between extremes in design. The shape varies according to the needs of the airplane for which it's designed. In flight, a wing is simply a streamlined object inserted into a moving stream of air. If the wing profile were in the shape of a teardrop, the speed and the pressure changes of the air passing over the top and bottom would be the same on both sides. But if the teardrop-shaped wing were cut in half lengthwise, a form resembling the familiar wing section would result. If the wing was then inclined upward so the airflow strikes it at an angle, the air moving over the upper surface would be forced to move faster than the air moving along the bottom of the wing. This increased velocity reduces the pressure above the wing. Applying Bernoulli's principle of pressure, which we discussed in the previous video, the increase in the speed of the air across the top of an airfoil produces a drop in pressure. However, the pressure difference between the upper and lower surface of the wing alone does not account for the total lift force produced. The downward and backward flow of air from the top surface of a wing creates a downwash. This downwash meets the flow from the bottom of the wing at the trailing edge. Applying Newton's third law, the reaction of this downward-backward flow results in an upward-forward force on the wing. Lift is also generated by pressure conditions underneath the airfoil. Because of the manner in which air flows underneath the airfoil, a positive or high pressure results. At a point close to the leading edge, the airflow is virtually stopped at a stagnation point, and then gradually increases speed as it moves further aft. At some point near the trailing edge, the airflow again reaches a velocity equal to the flow on the upper surface. Again, applying Bernoulli's principle, where the airflow was slowed beneath the wing, a pressure was increased and positive upward pressure was created. Both Bernoulli's principle and Newton's laws are in operation whenever lift is being generated by an airfoil. The angle of attack of a wing is the angle between the chord line and the flow of air against the leading edge of the wing. Experiments conducted on wind tunnel models and on full-size airplanes have shown that as air flows along the surface of a wing at different angles of attack, There are areas where the pressure is negative or less than atmospheric pressure, and other areas where pressure is positive or greater than atmospheric. This negative pressure on the upper surface creates a larger force on the wing than the positive pressure resulting from air striking the lower wing surface. The average of the pressure variation at any given angle of attack is referred to as the center of pressure, or noted as CP. All aerodynamic forces act through the center of pressure. At high angles of attack, the center of pressure moves forward, while at low angles of attack, the center of pressure moves aft. This center of pressure travel is very important, since an airplane's aerodynamic balance and controllability are governed by changes in the center of pressure. Now, the production of lift is much more complex than the simple differential pressure between upper and lower wing surfaces. In fact, many airfoils do not have an upper surface longer than the bottom. These are called symmetrical airfoils. Symmetrical airfoils are seen in high-speed aircraft having symmetrical wings, or on symmetrical rotor blades for many helicopters whose upper and lower surfaces are identical. With symmetrical airfoils, the relationship of the airfoil with the oncoming airstream, or angle of attack, is all that is different. As a wing moves through the air, it is inclined upward against the airflow, producing a different flow caused by the wing's relationship to the oncoming air. Think of a hand being placed outside the car window at a high speed. If the hand is inclined in one direction or another, the hand will move upward or downward. So far, we have only focused on the airflow across the upper and lower surfaces of an airfoil. While most of the lift is produced by these two dimensions, a third dimension, the tip of the wing, also has an aerodynamic effect. The high-pressure area on the bottom of an airfoil pushes around the tip to the low-pressure area on the top. This action creates a rotating flow called a wingtip vortex. That vortex flows behind the airfoil, creating a downwash that extends back to the trailing edge of the airfoil. This downwash results in an overall reduction in lift for the affected portion of the wing. Airplane manufacturers have developed different methods to counteract this action. Winglets can be added to the tip of an airfoil to reduce this flow. The winglets act as a dam, preventing the vortex from forming. Winglets can be on the top or bottom of the airfoil. Another method of countering the flow is to taper the airfoil tip, reducing the pressure differential and smoothing the airflow around the tip.